Dear students, welcome for new session. In the last class, we discussed the automorphism, define the what is automorphism, inner automorphism, outer automorphism, provide the examples of automorphism, and then we have to prove in the end one result of about the automorphisms. Okay, so now we have to this lecture start with this theorem with saying that any group of G inner automorphism is always a normal subgroup in automorphism of this G. So, inner automorphism is always a automorphism of a G. You know that inner automorphism we have a phi of A is the element of a G. This can be written as A inverse some G A and or you can just say that you can write as a G of A inverse. Okay, so now we have to show that this inner automorphism of a G is uh, in this inner of this is a normal subgroup of this automorphism G. So first we show that this inner is an group and also satisfy the normality condition, then we can say that. So for showing that the group, we take any two elements of a X and Y are the elements of a into this. The elements of this is the types of a phi of A and phi of B are the element of this inner of G, and then phi of A is can be written in the form of a X A inverse or A inverse X A. So we use both the conditions in the no problem. So phi of A is the element of inner of G, phi of B inverse is the element of a G. Then we have to show that this is equal to phi of A into phi of B ka inverse is also the element of a inner of a G. So let's start. We have to just say that first is a phi of A x is equal to, you have a x inverse A x, and phi of B is equal to B inverse x b, and then by the composition mapping of the previous theorem, if you remember, we have to just say that phi of A composition phi of A inverse is equal to nothing but is equal to phi of A inverse is equal to phi of E, and then phi of E is the element of a clearly is a element of a inner of a G. So this means at least we have to show that this clearly that this E is the element of a ing. So this means this we have to show that at least ing G is not equal to empty. So this means first is, we have to show that this is identity automorphism, and then we can say that this is clearly as inner of G is not equal to phi. So at least we know that this inner is not an empty set. And now if we show that this phi of B inverse is also in the form of this form, so this we can take a H is equal to phi of A, G is equal to phi of B, then we have to take a H of AB inverse is equal to phi of A, phi of B ka whole inverse over some X, and then we have a phi of B inverse, and then phi of B inverse A. And now just say that we can say that by the composition of this mapping, this can be written as a B inverse A inverse like this. We have to just take we just showing into this form. That means we have a okay, just this condition phi of A composition phi of B is equal to phi of B into A. So we know that the property of this clearly is saying that you have a phi of A composition phi of B is equal to phi of B A. So by this phi of A composition phi of B is the same as a phi of B A, and then you can say that this can be written as a phi of B inverse A, and then phi of B inverse A is nothing but is equal to again written in the form of a. So this is the element of a inner automorphism of G, and that means we can say that by this theorem can be using this here, and then we can say that H and the phi A. So this means we can say that phi of A and phi of B ka inverse is also belongs to this means we can say that phi of A, phi of B ka whole inverse is also the element of a inner of a G, and if it is inner of a G, then this clearly inner of a G is subgroup of this automorphism of a D. Okay, so now this first part is completed. Now we have to solve the second part. We have to show that the normality condition is also hold. So take phi of A is the element of inner G, and psi of A also the inner automorphism of G. This psi is automorphism of G. Then we can show that psi inverse phi if so we can show that psi inverse composition phi composition psi is equal to is nothing but is equal to, we can say that is the element of a again this inner of G. So by the property of a inner, we can just say that this can psi of apply here. So phi of psi of psi, and then psi inverse is equal to phi, and this by the property of this you have this. So you have just phi of A x is equal to, written in the form of a inverse x A. So this is in place of x we have a psi of x. So A inverse psi x A, and then this is nothing but is equal to, in place of this psi we can write as a psi inverse of psi. So we can just this psi is the element of automorphism of this, and then the psi is automorphism of this means is a also is a homomorphism. So this means psi of inverse of A, and the psi inverse of psi of x, and psi inverse of A, and psi inverse is equal to identity. So this can be written psi inverse of A then you have to write in this form. You phi of A ka phi of A inverse can be written in the phi of A ka whole inverse. So you can here psi inverse A ka whole inverse, and then this is identity I of x is equal to x. So this is equal to x, and then we can say the psi inverse of A, and then we have to just see this what is this. This is nothing but is equal to, in the form of a psi inverse of A, and then you have a inverse is equal to this composition, and then we have to using the definition of this. So phi of psi inverse is equal to A, and then we can say that if it is A, then this is nothing but is equal to in the element of a inner of a G, and this means this is the for x, and this means we can say if it is the inner of a G, then we can say that this composition is equal to is the element of inner of a G, and then we have to show that finding some psi belongs to the automorphism of G, and phi of A is the element of an inner automorphism of a G, then we have to show that the composition of this also the belong to the inner automorphism of G. So this means inner automorphism of G is clearly is a normal subgroup of a this group of automorphism of a G. So this completes the proof of this result. We have to show that this result clearly, if we have a inner automorphism of a G is always is a normal subgroup of automorphism of a G. So we shall show that automorphism is a group, and inner automorphism is a subgroup, and also is a normal into this. Okay, so now we have another result, and that result is saying that let G be a group, then the quotient group is isomorphic to inner automorphism of a G. So which has said that simply is equal to, if G is a group, then the quotient group G by Z is isomorphic to inner automorphism. So if we have to show that this is isomorphic to inner automorphism, that means there is a two method. If you have to show that there is a onto homomorphism exists, and then by using the theorem of first isomorphism theorem, then we can say that G by Z is isomorphic to in upon kernel of that element. Okay, so consider a mapping psi from G to inner automorphism of a G. Then we define psi of A. Inner automorphism is always the element of phi of A inverse types, and A is the element of phi of A is the element of a inverse of inner automorphism of a G. So now we have to consider into this thing. This we can say that if it is isomorphic, then we can say that G of kernel of this psi is by the first isomorphism. If it is onto homomorphism, then we can say that G upon kernel of phi is isomorphic to inner automorphism of a G, and then we have to show that kernel of this psi is equal to nothing but is equal to center of this group. So if we succeed to prove this part we have to this. So first we have to show that this is map we define is a well defined map. So this is psi we define is a should be a well defined, and then well defined means you take a is equal to b. So we take a in philosophy we take a is equal to, if we take a is equal to b, if a is equal to b, then by the uh, this can be written as a is equal to b, means we can say that can be written as a x a inverse is equal to, you have a bx b inverse, and this a can be written as a inverse to inverse x a inverse, can be written as a b inverse to inverse x b inverse, and then by this is nothing but is equal to, you have to just say that this is equal to phi of a inverse, and this is nothing but is equal to, you have a phi of a b inverse, and then phi of a inverse nothing but is equal to, you have a psi of a, and this is equal to, you have a psi of a b. So this completes the showing that this means we can say that this psi is a well defined, or you take a inverse b inverse, then you can again by this saying this these two are equal, then we can say that this is phi of a psi of b, and then phi of b is equal to this a inverse satisfy for a inverse condition into this form. Okay, so this means we have to write into this form. So this means this is phi of a psi of a, and psi of is well defined, and now we have to show that this is, I think, better we take a phi of a, not need of an inverse. If phi of a in automorphism of G, then psi of a inverse is equal to psi of a, then we have a clearly psi is an onto. So if we have taken a inverse, then this is equal to phi of a, and phi of a is clearly is onto. Okay, now we show that psi is homomorphism, then we can take phi of psi of AB is equal to phi of AB ka inverse, and phi of AB ka inverse, phi of B inverse, phi of A inverse, and then by the this property we have to take the phi of A composition phi of B is equal to phi of a B composition A. So by this condition phi of B composition A inverse, the phi of A inverse and composition phi of B inverse, phi of A inverse is equal to psi of A, phi of B inverse is equal to psi of B, and then by this result we have to clearly say that this can be written in the form psi of AB is the same as a psi of A and psi of B, and then these two are the same, then we can say that clearly psi is a homomorphism. So we prove that psi is also is a homomorphism. Okay, now we have to show that these two are onto and also homomorphism, and then this map we have to define it from psi, from we have to take a G to inner automorphism of a G, and now by the first isomorphism theorem is saying that G upon kernel of this psi is isomorphic to inner automorphism of a G. For complete the proof of this, we have to show that this kernel of a this psi is equal to, you have a nothing but is equal to center of a group of a G. So we have to only show that in this case we have to show that this map is this. So this means we have to just say that first thing is very clear, by the first isomorphism theorem we can say that G by kernel of a isomorphic could be this form. If we succeed to prove that kernel of a phi is equal to center of a G, then the theorem is complete proof. So let us try from this. So we take a kernel of a psi is equal to Z. So kernel of a psi is equal to A is the element of a Z, then psi of A is equal to identity of this map phi, and this is phi of E is the element of a inner automorphism of a G, and this is called is the identity element of this. So this means this is the identity element of this. Then this means phi of this is the phi of A inverse is the is equal to phi of E or phi of A, and then phi of A inverse can be written in the form of A inverse to inverse is equal to in this form, and then we have to A inverse x A and E inverse xa. So A inverse xa is equal to, you have to getting the x, and then we can say that Ax is equal to xa, and center of this is equal to this form. Okay, this can be written in the form of this also, we can just write in the form of this A inverse ka inverse x of A if is equal to E of we just write into the form of a this is E inverse x of E, and then we can say that this is equal to, you have a and we have this is a inverse ka because x a inverse, so this means x of a inverse is equal to, you have a x, and then you have to the x a is equal to ax is equal to, you have a x of a, and then we have to say that this is clearly into the z. So this means is not a problem. We have to taking a for a, so phi of a inverse is equal to, you take a inverse to the inverse x of a inverse, and then we have to show that into form of this uh, a is the element of a G, then ax is equal to x of a, and then this is nothing but is equal to center of a G. So by the isomorphism theorem, first isomorphism theorem, we easily show that G by ZG is isomorphic to inner automorphism of a group of a G. So this completes the proof of this theorem. Okay, let's move. We have to some examples by using this. G is a abelian group, then G is nothing but is equal to ZG, then inner automorphism is nothing but is equal to 1, and is noted earlier. We have to just say that identity is the only always is an abelian group is this, only the identity is a inner automorphism. Now we take some different example. We take a G is equal to S3, and now Z of S3 is equal to, you have a clearly is equal to identity element center, no other element is commute. This means, so we can say that because it's a non-abelian group, and then we have a the size of a Z3 upon S3 is equal to 6. So there are 6 inner automorphism of S3, and different elements of S3 give rise a distinct inner automorphism. And now because we have a this is clearly we have 6 different inner automorphism of the, because size of this is equal to, because by the previous result we can say that this S3 upon center of a S3 is isomorphic to inner automorphism of G. So if it clearly is a inner automorphism of this G, so there is a possibility of this size of this is equal to 6. So there is a possibility of a 6 inner automorphism of S3, and we have to get a different S3 gives rise the different distinct element of automorphism. For example, if we take and now we show that this is clearly phi of 1 2 phi of 1 3 over 2, and then we can write into this form of a phi of 1 2, then we can be written as the form of a phi of 1 3 over 1 2, and this can be written as a phi of 1 2, then you have a 1 3 ka inverse, then 1 2, and then 1 3, and now we have to calculating this 1 3 ka inverse is also is a 1 3, so this means phi of 1 2 1 3 ka inverse you have a 1 3 itself, and then you have a 1 2, and then you have a 1 3. And now if you calculating this, you have to just check there is a 1 goes to 3, 3 goes to 3, and 3 goes to 1, so 1 goes to 1. Now 2 goes to 2, 2 goes to 1, 1 goes to 3, so 2 goes to 3. So only possibility of this phi of 1 2 is equal to 2 3. And now if phi of 1 2 is equal to 2 3, then we have to calculating into this again. If you calculating this again, you have to just take into this form. You have a 1 2 ka inverse, then you have a 2 3, then you have 1 2, again 1 2 ka inverse, you have note that 1 2, and then you have a 2 3, and then you have a 1 2, and then again you have to just check 1 goes to 2, 1 goes to 2, and 2 goes to 3, and you have a and 3 goes to 3. So this means we can say that clearly this is equal to okay, in this coin we 1 2, and then you have a 2 3 and 1 2, and this is nothing but is equal to is giving you a 1 2. Okay, so you have a 1 goes to 2, and you have a 2 goes to 3, and 3 goes to 3. So this means simply is equal to 3 goes to 3, and then we have a 1 2 is in the form of this. So, this is giving you a 1 2, and then if you take a 1 3 1 3 1 2, then this is 1 2 not 3. Okay. So, this 1 3 1 2 is a not equal to 1 2 1 3. So, this means we can simply say that this is not a clearly not an automorphism. So, this means clearly the non-abelian thing is there. We just say that this clearly, this is I think is 1 3. I just check. Okay, just we have to just check. We have a take a composition 1 2, and then you have a 2 3 and 1 2. So, we have a clearly is a 1 3, not this. I just check. 1 goes to 2, and 2 goes to 3, and 3 goes to 3, 1 goes to 3, and then 3 goes to 3, 3 goes to 2, and 2 you have a 2. So, 2 goes to 1, 1 goes to 1, 1 goes to 2. So, this is equal to 2. This is 1 3, not a 2. Okay, this is 1 3, and this is clearly 2 3, and these two are clearly not the same. So, this means we can say these two, we have to calculating these two is not equal to the same. So, in this case we can say similarly this is a inner automorphism non-abelian group of order 6. So, this means clearly inner automorphism of S3 is always isomorphic to S3. Okay, now just try one more example. I think automorphism of Z10 is isomorphic to U10. U10 is equal to, you know, that the 1 2 3 all these elements. So, we try to find there are only two groups of order 4. There is a possibility for this is the size of a U10 is equal to you have a 4, and if it is a 4, then there is a only possibility is Z4, and you have a Z2 cross Z2. There is only possibility of there are only two groups of order 4, including Z4 and Z2 cross Z2. And now, if you take 3 square is equal to 9 under modulo 10, so this means under modulo 10, this means 3 square is equal to 9. Since 3 does not have a order 2, it follows that Z10 is not equal to this thing. So, this means clearly in Z10 there is a one element we can find is a 3, and 3 square of a 3 is equal to not a identity. So, 3 does not have an order 2. So, this means we have does not say that this can be automorphism Z10 is equal to the Z2 cross Z2. Now, another possibility is this. So, that therefore, only possibility is this. We have only two possibilities are there, Z4 or Z2 cross Z2. So, this is ruled out. Then only possibility is this automorphism of Z10 is isomorphic to Z4. So, this means automorphism of I10 is always isomorphic to Z10 is isomorphic to Z4. Okay, so just one more example. U8 is isomorphic to U12. So, you just find the we try to find the U8 is isomorphic to U12, then you find the element of a U8 is equal to 1 relatively prime to 8 1 3 5 7, and then U12 is relatively prime to 12 1 5 7 11, and then both the element of a U8 and the size 4 and also U12 is also size of 4. Now, for isomorphic showing isomorphic, so we have to take a bijective map from phi U8 to U8 to U12 and defined by because we have 4 elements are there, phi 1 always, you know that the phi of 1 is always mapped to identity of this. So, identity of this set is equal to 1. So, this is phi 1 is always mapped to this. Now, we have a 3 5 7, and now you just check this means phi of 3 is equal to, I just said that for 11, and then phi of 5 is equal to 5 and 7 is equal to 7. So, we just take for this 5 map to 5, 7 map to 7, this maps 3 is mapped to this 11. Okay, because you just know that if you take a 3 square is equal to you have a 9, and that means equal to 1. So, this is the order of a 2, and then if you take a 11 square is equal to 121, and then you have to again identity 1. So, this means order of a 3 is the same as a order of 11. And similarly, if you take all of them, we have to take in the form of this. So, clearly this means phi of 3 is going to the phi of 11. We claim that it has a operation preserving property because U8 is an abelian group, so it is suffice to check following. So, we have a phi 3 is equal to same as a phi 1, and 11 is also the same, and then 5 square is equal to also order 2, and this is again you have a order 2, and then if you had a composition, phi of 3 into 5 is equal to by the composition of because we have to Z8. So, we have phi of 7, and phi of 7 we have to have 7, and then 7 can be written as 11 into 5, 5 3 into this. So, phi of 3 7 can be also into this form. Phi of 5 5 is equal to we have a 5 because 21 divided by 8 is remainder is 5, and 5 can 11 into 7. If you 11 into 7 is equal to you have a 77, and then you have a 12, and then again you have 5 remainder, then you have you can write in this form, and similarly this can be written in this form. So, in general you may show that any bijective from U to 8 with phi is equal to 1 is a isomorphism. So, we clearly show that here this satisfy all the properties of this isomorphisms. We have all the this is satisfying the homomorphism conditions, and then all the groups are the if we take a this is equal to identities, and then satisfy the condition all the groups of this order of preserving, and inverse is also there, bijectiveness is there. So, this means this satisfy the condition of this isomorphism. So, we have to show that if we have a group of this U8 to U10 are clearly isomorphic. So, U8 is isomorphic to U10, sorry 12, U12. So, U8 and U12 are isomorphic to each other. Okay, now I just to stop this lecture here. So, today we have to discuss the properties of automorphisms, and then we have to define the what is our inner automorphism. After defining the inner automorphism, we discuss the property and then show that the quotient group of G by ZG is always isomorphic to inner automorphism of a G, and we show that inner automorphism is also is a normal in automorphism of a G, and then finally we have to prove one result. We show that this automorphism of Z10 is isomorphic to Z4, and also the last is U8 and U12 are isomorphic to each other. So, that means this is the all we have to this into this portion. So, now in the next class we discuss the Cayley theorems, and then we have to complete this portion, and then we have to move to the our next section of this group theory is a last part of the this course is about the direct products of a group. So, we try to define two different types of direct products. One is a internal direct product, another is a external direct product, and when we say that both are internal and external direct product are the same, and what condition this thing. So, I just stop this lecture here. We continue in the next class for Cayley's theorem. Thank you very much.